Good evening students, I am Dr. Ganesh Kumar Patel and welcome to Radiation Oncology course. This is the lecture number 33 and the topic of lecture is the radiation safety part 3. So with my previous lecture we understand what is the personal monitoring service, a personal monitoring system, and in personal monitoring system we started to understand what is thermoluminescence dosimeter. TLD is a passive type of detectors and we understand how the TLD, the principle of TLD, how TLD principle of working we understand. In short, we just recapped. TLD works by storing the energy they receive from the ionizing radiation, which is constantly exposed by the radiation worker in the field of radiation, until they are heated to a higher temperature around 250 degrees Celsius. This is going to happen in a TLD reader, which we will see further. And on heating, the absorbed energy is released in the form of visible light. Then visible light is recorded. That visible light recorded is the recorded dose, and a plot of light intensity emitted against the temperature is drawn, and that drawn curve is called glow curve. This glow curve helps to understand the thermoluminescence intensity, and with the help of this glow curve you find out your required dose. Means this is the experimentally calculated. And how this process happen? This process happens in a dedicated laboratories which is authorized by Atomic Energy Regulatory Board, which is a regulatory body of India. There are 4 laboratories all over India, and they have been divided according to the zone. There are north, south, east, west. And according to the area where your hospital lies or your institution lies, in that area you need to send your TLD cards for the process and to get your dose record. So they have a TLD recorder. In that TLD recorder there is a photo multiplier tube. I will give the overview. There is a photo multiplier tube and there is a heating cycle controller, and here you can see there is a glow curve, and here it is a dose meter which measure the dose, and here it is a oven and thermocouple device and optic filters, because you are going to receive in the terms of visible light and your signals. So this is a basic architecture of a TLD reader which process your TLD and gives you the dose report or dose of individual. Now how the TLD batch looks like? This is the TLD batch. You can see that this TLD batch looks like this. This is a crocodile pin. This is a plastic material, and these plastic material front view have a 3 windows, 1, 2, 3. In these 3 windows, when you are separating out this, you will see that upper area, this is your chip. This is the material where in this black polythene the material lies, and this is the back side of the batch. This is a filter. Okay, BRC full form is a Bapa atomic reaction. This is a front cover, back TLD, and this is a TLD chip. TLD chip containing a CSO4 material with dysprosium doping. And here you will find the TLD batch number. TLD batch number consists of institution number and the C for chest, because this is a chest batch, and the individual's number. Then the name of a person, then name of institution, and most important type of radiation, because your TLD batch is able to record a dose from gamma radiation and X-rays. So it is written here G plus X, and the quarterly is the service of which quarter service. Here it will mention the quarter service name, July to September, January to March, and the name of the laboratory. This is the Ultratech Laboratories. That is the name of the laboratory. So this is the simple overview of a TLD batch. But as I said that previously there was an old system of recording a dose that is also passive, that is a film batch. I will just show you that how the film batch well looks like. Film batch well looks like they have a 6 windows. This is different from this. They have a 6 windows, and in this batch there is a film. There is a radiographic film was placed inside that, and that radiographic films have been divided into 6 compartments, 1, 2, 3, 4, 5, 6, and each compartment will have a 6 type of filters. Like first is a open window, means there is a open window, there is a nothing is there, just open window. Another was the plastic window. After that there was a cadmium window. fourth there was a thin copper, fifth there was a thick copper, and lead was the sixth copper. So why these the different types of filters are there? Because the radioactive material emits alpha, beta, gamma radiations. Your X-rays, radiation generating equipment produce X-rays, and some X-ray photons or some gamma ray photons have some lower, some have a low energies, or some have a high energy. Low energy means some have a primary photons, some have a scattered photons. So according to the origin, the energy of particles are different. So to measure the dose from all such a particles, means there are some low beta energy particle, low energy beta particles, high energy beta particles. So these windows have been made like alpha particles have a lowest penetrating power. So for such alpha particles there is a open window option is there. For plastic, like a perspex sheet, where low energy beta particles cannot penetrate, but high energy beta particles can penetrate. Then the thin copper is there, thin copper, thick copper. Lead is for highly penetrating radiation like X-rays. So in this way, for different types of energies, the different filters are used for recording the dose. In this case, TLD batch have only 3 windows. The first window is your this copper window. Okay, another window is a perspex sheet, and third is the open window. So you can measure from alpha particle to low energy beta particles, high energy beta particles, low energy X-rays, and high energy X-rays. These all things can be measured by this your material. So inside the look how it is looks like, the metallic which we have seen that is a combination of copper plus aluminium. On front side it is a aluminium, and back side it is a copper. So yes, backside it is a copper. Such a combination is here, and there is a plastic filters like a perspex material, and there is a open window, and there are 3 disc lies. These are the Teflon coated disc, means there are Teflon coated, but the inside material is CSO4, and these are 3 Teflon coated disc which are placed like this. This is the front side, and this is the back side, and it is a nickel coated aluminum plate. There is a plate inside. When you just remove this black polythene, there is a nickel coated plate is there, having a notch for the orientation, to know the orientation. And on this nickel coated plate, these 3 discs are mounted. These 3 discs are mounted containing a CSO4 material. So this is the internal side of a TLD batch. After that, the next personal monitoring service device is a pocket dosimeter. This is a digital pocket dosimeter, and this is a conventional pocket dosimeter. Here you can obtain the value of your exposure in digital form. Here there is a manual values. You can see that, means you cannot, there is no digital value. You will have a arrangement to know the radiation level. There is a scale, reticule is there, which you cannot see in this diagram, but there is a reticule scale where you can see the readings, manual readings. So radiation dose to person can also be assessed by wearing a pocket dosimeter. It is an active detector, as I said. You can get a immediate radiation level. Pocket dosimeters are very useful in certain operations where the radiation levels vary considerably and may quite hazardous. They give a spot information. Yes, pocket dosimeters are available for determination of the exposure up to 2 milligrade to 50 milligrade and 100 milligrade, or in terms of Roentgen, 200 mR, 5 mR up to 10 R Roentgen. Such a high level of radiation can be measured by a pocket dosimeter. This is a manual. There is a simple scale in this case. Here there is a simple scale here, and in this scale you can see the radiation level in this manual pocket dosimeter. The pocket dosimeter have a built-in capacitance which can be charged by external potential, and when exposed to radiation, the ionization produced in the chamber and decreases the voltage across the capacitance. It is based on simple electrical concept. There is a capacitor. When it is charged, the potential because of the external potential and exposed to radiation, ionization produced in the chamber and decreases the voltage across the capacitance, and the decrease or increase can give in the form of radiation level. The reduction in the voltage across the capacitance is a measure of amount of radiation and hence the quantity of radiation exposed. The another is the area monitoring. We understand the personal monitoring, but the another important thing is the area monitoring. Area monitoring is it means that where there is a radiation generating equipment is located, or a radioactive source with equipment, a sealed source or a unsealed source been located, the surrounding area is hazardous, or surrounding area is at a risk if there is, if the unknown persons or not person with knowledge of radiation can accidentally enter into that area and can expose to the undesired radiation. So to prevent such undesired radiation by even known or unknown person of radiation should be alarmed or should be informed through the area monitoring. And for this area monitoring, the devices which is used are called the area monitors. So this is an example of a gamma zone monitor. This is named as a gamma zone monitor. Gamma zone monitor is called area monitor, and another is a fluid biomedical based a radiation survey meter, ion chamber based survey meter. This is a ion chamber based survey meter, and this is a GM counter based survey meter. We already discussed how many types of detectors are there. So this is called a gamma zone monitor, and in this gamma zone monitor the detector which is used is the GM counter detector, and this is a fluid biomedical radiation survey monitor, and this is a ion chamber based detector. The detector is usually placed here. You can see here there is a detector. So normally area monitoring system should be able to determine the radiation levels in the range of 2 microgray per hour to 50 milligray per hour, or 0.2 mR to 5 Roentgen per hour, and also have a audio indications. So what happened in area monitors or area monitors, they have some predefined alarms. Predefined alarms, it means that the radiation level which is harmful for a radiation worker as well as for a common public, if by chance there is a mishappening or accident happened and the radioactive source came out of the shielding and remain out of the shielding for a longer time, so radiation level increases, then that at such a radiation level this monitor starts alarming. So it's alarming and saying that the radiation or the radioactive source is out of safe. It is in out of safe, out of shielding. So this is very important feature of this area monitors. This is happened with this monitor, this gamma zone monitor, area monitor, not with this monitor. With this monitor also there is a alarm, but you can change the means, yes, it is there also. In both this case there is alarm system is there. So the most commonly used area monitor has either a miniature GM counter or ionization chamber or a proportional counter. Mostly available are using GM counter and ionization chamber, making useful over a wide range of exposure rates. So for radiation survey of telecobalt and linear installation, ion chamber based survey meter is recommended. So this survey meter is recommended for radiation survey installations of a telecobalt machine or a linear accelerator. Now this is the table showing the different types of detectors and what they measure. GM counter is a 8-inch sight window. Its ionization chamber is cylindrical in nature. Scintillator is different shapes. What they detect: X-rays, alpha, beta, gamma rays. GM counter. Ionization chamber also X-rays, gamma, beta, alpha ray. Range is 2 to 20 mR per hour. The ionization chamber is the highest range. No, so the range is lesser than the GM counter range. Sorry, highest range, that is and marked by different names. So this is the simple explanation. Now we will understand the organizations which works in the field of radiation worldwide. The most important organization in the point of radiation safety and protection, and who is responsible for the safety and use of radioactive materials, even it is used in nuclear power plants or nuclear weapons, is the IAEA, International Atomic Energy Agency. It is widely known as World's Atoms for Peace and Development organization within the United Nations family. The IAEA is the International Center for Cooperation in the Nuclear Field. The agency works with its member states and multiple partners worldwide to promote the safe, secure, peaceful use of nuclear technology. India is also a partner of these organizations to use the radiation applications for the humanity, and it is located at Vienna. The second important international organization is the ICRU, International Commission on Radiation Units and Measurements. It is its purpose to develop and promulgate internationally accepted recommendations on radiation related quantities and units. I think this is explained by Professor Abhijit Mandal in his lecture, the importance of ICRU, and he has explained you the various types of radiation quantities which are derived by the ICRU. So this is located at Bethesda, USA. The next international organization is the International Commission on Radiological Protection. This organizations defines or provide the various recommended dose limits for a radiation worker, for public, for trainees, for pregnant women, and following this, following the whatever they recommend the dose limit for the professionals. The national regulatory body follows this organization to define the regulatory limits or dose limits at their national level. So this is very important organization for radiological protection point of view. After that, in India, Bhabha Atomic Research Center, I said that Bhabha Atomic Research Center scientists have developed the thermoluminescence material. It is located in Mumbai. It comes under Department of Atomic Energy. Its core area of research is nuclear physics, nuclear research, and located in Mumbai and Anushakti Nagar. And the most important thing, organization for our point of view, is the Atomic Energy Regulatory Board. It comes also under DAE, Department of Atomic Energy. It is constituted on 15th November 1983, located in Mumbai, head office in Mumbai, Anushakti Nagar. Its main purpose is to develop safe policies in nuclear, radiation and industrial safety areas for the facilities under its purview. ARB is not limited for the applications in medicines. ARB regulates all kind of applications of radiations taking place in our India, whether it is a nuclear power plants, whether it is a reactors, whether it is a nuclear ionic gauges which is used in oil welling, or it is in industrial applications, or it is in nuclear medicine. Everywhere where there is a use of radioactive, all comes under the control of Atomic Energy Regulatory Board. It develops the safety codes, and guides and standards for designing, construction, commissioning and decommissioning of different types of nuclear facilities, radiation facilities. ARB grants the permission or licenses for the applications of. Without the license or approval from ARB, it is illegal to use any radioactive source or any application of radioactive source or radiation generating equipment within India. So another one more organization is the BRIT, the Board of Radiation Isotope and Technology. I said you that in radiotherapy there is a telecobalt machine which uses a cobalt source. In India, previously cobalt sources, which is a radioactive source having half-life of 5.26 years, and cobalt source of 10,000 curies, such a high amount of activity has to be installed or has to be loaded into this cobalt machine, which is quite dangerous for safety point of view, was imported from other countries. But now in India, BRIT is able to produce such a high activity sources, which is applications in medicines. They also produces other radioisotopes used in research. So their main purpose is to produce a radioactive isotopes or radioactive sources. It is an independent area and located at Mumbai. Cobalt 6 are provided by BRIT. BRIT is also perform radioactive. It is also perform the waste management facility. They only have the waste management facility in India. So any sources which are going to dispose in India, it has to go to BRIT. Now the main topic we are going to start is the radioactive waste. As we learned in medicine or field of medical, there is a biomedical waste. The significance of biomedical waste is very important in medical field. Similarly, the importance of radioactive waste is also very crucial. It is radioactive waste is any material which is either radioactive itself or is contaminated by radioactivity, or for which no further use is planned or considered. So any material which is radioactive or which is having induced activity or which is unused should be considered as a radioactive waste, and it has to be disposed. So according to ARB, there is some guidelines which is under rules 1987, and we will discuss in details about the regulations of ARB in chapter of acts regulations of ARB. So radioactive waste means any waste material containing radioactive nuclides in quantity or concentration as prescribed by competent authority. These radioactive wastes are leftovers from the use of nuclear materials from production of electricity, diagnosis, treatment, disease and other purposes. We must understand the radioactive waste has been classified in three forms: the physical form, the activity level and the half-life. As you understand what is the radioactivity and what is the half-life in lectures by Professor Mandal sir, the physical form is again subdivided into the solid form, liquid form and gaseous form. Out of these, the most harmful form is the gaseous form and liquid form, which we will discuss further. Activity level: low level activity waste, intermediate level activity waste and high level activities. This is most harmful, high level of activity waste. Half-life: short half-life, long half-life. This is dangerous. So this category is really very dangerous when we talk about the radioactive waste, and special rules and regulations are there for such a management of such a radioactive waste. So ARB classification again is solid, liquid waste according to gaseous category. They have category 1, category 2, category 3, category 4. So category is depends upon the exposure rate. So as the exposure rate is increasing, the category increasing. Here liquid is also based upon the becquerel per milliliter. This is a unit of activity based. Liquid is based on activity. Solid lead is based on exposure rate, liquid is based on activity, and gaseous concentration is also activity based. In this ways it is classified: radioactive waste material, solid, liquid, gas. Basic approach in radioactive waste management. This is the important slide. This you should remember, it's like a thumb rule: delay and decay, because radioactive material have a half-life, and with time they decay, and as they decay their concentration of activity reduces, and as the concentration of activity reduces the strength of source decreases, and it becomes of no use. But it depends upon source to source. Some sources have years of half-life, some sources have short half-life, some sources have high half-life. So depends upon the type of source. Delay and decay: based on the fact that radionuclide loses their radioactivity through decay, suitable for waste those having a short half-life. So this delay and decay concept is suitable only for a radioactive material of short half-lives. Radioactive waste stored for minimum period of 10 half-lives. So any material which is having a short half-life like F18, like iodine 131, which is used in nuclear medicine departments, and iodine 131 is having a half-life of 8 days. Such a radioactive material can follow this principle of delay and decay with at least half-life of 10 half-lives. It is almost negligible and can throw into a ordinary sewage also. So dilute and disperse. The next is the dilute and disperse. Based on the principle that environment has finite capacity for dilution of radionuclide to innocuous level suitable for low level activity, dilute and disperse. Concentrate and contain. Based on the principle that some radionuclide take long time to decay. This is for a long half-life radioactive material. Thus, this waste needs to be contained for extended period of time, suitable for high level of activity and for long half-life waste. So this is for especially for a solid waste with a long half-life. In case of our like cobalt 60 sources or iridium sources, which are a half-life of 5.26, or cesium 137 sources, such a sources have a concentrate and contain type of principle for management, waste management. Steps involved in radioactive waste management is the pre-treatment, treatment and conditioning involves collection, segregation, chemical adjustment, decontamination, and may also include a period of interim storage. Treatment involves changing characteristics of waste by volume reduction, radionuclide removal, or change of composition. And conditioning. Conditioning involves transformation of radioactive waste into form that is suitable for handling, transportation, storage, and disposal. Storage involves isolation of radioactive waste to protect the environment and to control its disposal. It may take place at any step in radioactive waste management. Disposable. Final step waste management involves deposition of radioactive waste packages in disposable facility like BRIT in India with no intention of retrieval. It may also include discharging radioactive wastes such as liquid and gaseous effluents into environment within authorized limit. Collection. Okay, disposal. Very important thing is that disposal cannot be like a ordinary dustbin. Like in medicine, the biomedical waste also have a categories of dustbins. Similarly, radioactive waste should be placed in a specialized dustbin or specialized bin. You can see in this figure, this is not accepted, this is the accepted, which should be pasted with a radioactive symbol which I have seen, and it should be made up of a lead material with a sufficient shielding, so that it depends upon the material which is going to be disposed or which is going to be stored for a long time. So the collected radioactive waste is disposed as per the following: delay and decay, dilute and disperse, concentrate and contain, which already discussed. Special situation of a radioactive waste management. Disposable of sealed sources. In radiotherapy, we know that there is a use of sealed source like iridium-192 source, cobalt-60 source, cesium-137 source. So for such a sealed sources, even blood irradiators, some blood irradiators were previously using or right now also using a radioactive source, but some blood irradiators are coming with X-ray generator based. It involves use of sealed sources. Once the sources become weak means the activity is below its application. So like in iridium source, the loading activity is 10 millicurie, but the source when reaches to 1 millicurie, it has no applications for the clinical purpose. So this is called a weak source or low activity. It is returned to the supplier for its disposable. Disposable of excreta and urine of patients administered high doses of radioactivity. This is the case of nuclear medicine, where patients have been treated with iodine therapy. So we will not going to discuss this about the iodine therapy. Management of cadaver. Cadavers containing cadavers means the patient who received the radiation treatment through ingestion or through administration, and he died with activity. Such a patients are how to handle such a patients. If activity is concentrated in few organs of a patient who died, then same may need to be removed by autopsy, or body may be handed over after ensuring that it do not exceed the recommended dose limit, which is generally public dose limit. In case of widespread disease where organ removal may not bring down the radiation level to accepted limits, the body may be introduced into a plastic bag and stored in a mortuary cold room for a physical decay and its radiation level come down. The delay and decay, it's a very simple rule. These are the examples of short-lived radioactive sources which is used in for the treatment, nuclear medicine. Disposable of solid waste. This is important in terms of radiotherapy. So low activity waste comprising of paper tissue, swabs, glassware, which are low activity with ordinary refusals. The waste do not go through. Dumping in garbage several is not recommended for disposable of solid waste. Solid waste should be buried in the ground. Disposable of solid waste by burial needs an exclusively buried ground satisfying following condition: isolated site, fence to restrict the entry, because whatever the sources, solid sources which needs to be disposed either in India or outside the India, they have a common conditions or common criteria. That criteria are the isolated sites, fence to restrict the entry, approved by competent authority of the national or depends upon the nation, not more than 12 burials in a 1 year. Distance between the successive pits where the radioactivity is to be placed 180 centimeter. Top layer of the pit should have at least 120 centimeter thickness of the compact earth. Once closed, the pit is not open for use for 10 half lives. The excavated material from a closed pit released for a disposable under the supervision of radiological safety officer. Total activity of the waste buried in any one pit should not exceed the some restricted limits by regulatory body. So this is the radioactive waste management we understand. So thank you students.